Hi, I'm Dr. Incognito. In this video, we're going to investigate alternating series, and we're going to discuss absolute convergence and conditional convergence. So first, suppose we have a series of the form summation n equals 0 to infinity of -1 to the n times a sub n, where we'll assume that the a sub n's are all positive. This is called an alternating series because as n alternates between even and odd, 0, 1, 2, 3, n will go even, odd, -1 to the power n is going to alternate back and forth between +1 and -1. So this series is going to have the form a sub 0 minus a sub 1 plus a sub 2 minus a sub 3 plus a sub 4, etc. So this is called an alternating series. Because the sign of the terms is alternating. So now to discuss the convergence of an alternating series, there is the alternating series test. And it says, first, if the limit as n goes to infinity of a sub n is equal to 0, and the a-n's are decreasing eventually, then the series will converge. Then the alternating series converges. So you need two conditions. If the limit as n goes to infinity of a sub n is 0, and if the a sub n's are decreasing eventually, then the series will converge. And note on this first condition, if the limit as n goes to infinity of a sub n is not 0, then the series will diverge. Then the alternating series will diverge by the test for divergence. By the test for divergence. If the limit of the terms of a series is not 0, then the series will diverge. So let's look at some examples. First example, a category called alternating p-series. Alternating p-series. So those are the summation n equals 1 to infinity, -1 to the n plus 1, times 1 over n to the p. So here I've put -1 to the power n plus 1 because my n is starting out with an odd. So n plus 1 here will start out with even and will begin with a plus. It's not terribly significant, but it's always nice to begin with the plus. So 1 over n to the p, where p is any positive power. This is called an alternating p-series, and it turns out that an alternating p-series will always converge because it will satisfy these two conditions. A sub n is equal to 1 over n to the p, and so the limit as n goes to infinity of 1 over n to the p is 0. Remember, p is a positive power, so n to the power p is going to infinity. Its reciprocal is going to 0. And also, if you look at a sub n plus 1, that will be 1 over n plus 1 to the p. That will be less than 1 over n to the p, because n plus 1 is bigger than n, so n plus 1 to the p will be bigger than n to the p, so its reciprocal will be smaller. And this is, of course, an. So a sub n plus 1 is less than a sub n. That means that the a sub n's are decreasing. So from the alternating series test, we can see that this is more or less our simplest example of an alternating series. We can see that it converges. The limit is 0, and the terms are decreasing. So an alternating p-series will converge for any value of p bigger than 0. So let's look at a more intense example. Suppose that we have the summation n equals 1 to infinity, negative 1 to the n plus 1 times n squared over n cubed plus 1. Here we have an alternating series. If we take the limit as n goes to infinity of a sub n, that's the limit as n goes to infinity of n squared over n cubed plus 1. And here we do have an infinity over infinity. We could use L'Hopital's rule a couple of times to see the answer, but the general rule when you have a limit of polynomials is that the bigger power will dominate. So we have n cubed on the bottom and only n squared on the top. So relatively speaking, the bottom is going to be much larger than the top as n grows. So this is going to be 0. And secondly, the idea of comparing an plus 1 directly with an with these complicated fractions might not be a good one. So instead what we'll do is we'll create the function f of x equals x squared over x cubed plus 1, and we will try to show that f prime is negative eventually. So that if f prime is negative, then f will be decreasing. So what is f prime of x? We'll use the quotient rule, which is going to give us a perfect square in the denominator. So we're really interested in the numerator. It'll be x cubed plus 1 times 2x minus x squared times 3x squared. And if we simplify that numerator, the numerator has 2x, and then plus 2x cubed, 2x to the fourth minus 3x to the fourth gives us minus x to the fourth. And that's going to be negative if x is bigger than or equal to 2, because the numerator, we could take out a 2x, and we're left with, no, we could take out an x, excuse me, and we're left with 2 minus x cubed. And on the bottom we have this perfect square. This is going to be negative if x is bigger than or equal to 2. If x is bigger than or equal to 2, this is positive, and the denominator is positive. And 2 minus x cubed, if x is 2, that's 2 minus 8, that's negative. And if x is bigger than 2, this x cubed only becomes bigger, so 2 minus x cubed will be negative. So this is negative if x is bigger than or equal to 2, which means that f is decreasing if x is bigger than or equal to 2, which means that the ANs are decreasing for n bigger than or equal to 2. So that satisfies our ANs are decreasing eventually. So ultimately then, by the alternating series test, the series that we have there converges. Okay, so there's a look at the alternating series test. Now let's look at what's called absolute convergence versus conditional convergence. Absolute versus conditional convergence of an alternating series. Absolute versus conditional convergence of an alternating series. So here we have a standard alternating series. And the ANs are all positive, so we have A0 minus A1 plus A2 minus A3, etc. The plus-minus effect is going to actually make it easier for the series to converge. It helps for the convergence. So the question is basically, in absolute versus conditional convergence, the question is, if we remove the plus-minus effect, does the resulting series still converge? So suppose we're given an alternating series. If the series n equals 1 or 0, I have here, to infinity, if this converges, so if our alternating series converges, even if we remove the alternating symbol here, minus 1 to the n, so So now this is just a series of positive numbers. If this converges, then we say that the alternating series converges absolutely. The word absolutely coming in here from absolute value. If you take the absolute value right here, that will remove the alternating symbol there. And in this case, when we say that the alternating series converges absolutely, that is an example of convergence. So the alternating series does converge. Now, on the other hand, if you remove the plus-minus effect, maybe the resulting series diverges, and in that case you'll get conditional convergence. So in other words, if the alternating series does converge, if that's known to converge, but the resulting series without the alternating symbol diverges, then we say that the alternating series converges conditionally. So let's look at a couple of examples. A moment ago we talked about alternating p-series. Alternating p-series, the summation negative 1 to the n times 1 over n to the p. These always converge. So if p is bigger than 1, then the series 1 over n to the p converges even without the plus-minus effect, which means that the alternating p-series converges absolutely if p is bigger than 1. And on the other hand, if p is less than or equal to 1, here p is positive in the alternating p-series, if p is less than or equal to 1 but positive, then the p-series diverges. But the corresponding alternating p-series converges, so this means that the alternating p-series converges conditionally if p is less than or equal to 1. As another example of this conditional convergence, let's look at the more complicated example that we had on the board a moment ago, the summation of n squared over n cubed plus 1. A few moments ago we said that this converges. Does it converge conditionally or absolutely? So if we remove the plus-minus effect here, then we get the series summation n squared over n cubed plus 1. N equals 1 to infinity. And this one, from our experience with the limit comparison test, this one is like the harmonic series, summation n equals 1 to infinity of 1 over n, the harmonic series. And the harmonic series is known to diverge. So here, to see that the convergence is conditional, we need to show that this series diverges. This series will diverge by, we could use the limit comparison test with the harmonic series. I won't go through the details here, but if we use the limit comparison test with the harmonic series, then we will conclude that this series diverges. And so the conclusion for this discussion is this alternating series does converge, but it requires the alternating symbol here for the convergence. If you were to remove the alternating symbol, then the resulting series would diverge. So in that case, we say that this alternating series converges conditionally. Okay, so there's a look at alternating series, absolute convergence, and conditional convergence. I hope you found this video to be helpful. Thank you.